Chapter 1: Shadows in the Cosmos. To understand the universe, we must look not only at what shines, but also at what hides. Let's begin with what we can see. When we look up at the night sky, we see stars twinkling like tiny lights in a vast sea of darkness. We see the moon, sometimes a full circle, sometimes just a sliver. With telescopes, we see distant galaxies, glowing clouds of gas, and sometimes even exploding stars called supernovae. All of this, the shining, the glowing, the brilliant, is what we call visible matter. For a long time, scientists believed this visible matter was everything. It seemed obvious. If we can see it, we can study it. And if we can study it, we can understand it. But then something strange happened. In the early 1900s, scientists began to notice that some things in space didn't behave the way they were supposed to. Galaxies, those enormous collections of stars, were spinning much faster than expected. According to the rules of gravity, the stars near the edge of a galaxy should be moving slower than the stars near the center. But they weren't. The stars on the edge were moving just as fast, sometimes even faster. If galaxies were made only of visible matter, those outer stars should have been flung away into space. But they stayed in place, orbiting the galaxy as if something invisible was holding them in. This invisible something was not just a small detail. It had mass. It had gravity. It was keeping entire galaxies together. In 1933, a Swiss astronomer named Fritz Zwicky was studying a group of galaxies known as the Coma Cluster. He looked at how fast the galaxies inside this cluster were moving. They were moving so quickly that the visible matter couldn't explain their speed. It was like watching cars drive around a roundabout at full speed with no guardrails, and somehow none of them flew off the road. There had to be something else holding them in. Zwicky called this missing substance dark matter. Dark because it didn't give off light. Matter because it had mass and caused gravity. At the time, many scientists didn't take him seriously. Zwicky had a difficult personality, and some people thought he was exaggerating or miscalculating. But even if people didn't believe him right away, his idea had planted a seed. Decades later, in the 1970s, a female astronomer named Vera Rubin picked up where Zwicky left off. She and her colleague Kent Ford were studying the motion of stars in spiral galaxies. Using better instruments and more careful observations, Rubin found something surprising, something that matched Zwicky's earlier work. She confirmed that stars far away from the center of galaxies were moving much too fast. There had to be more mass, a lot more, that they couldn't see. Rubin's work changed everything. It wasn't just one galaxy behaving strangely. It was happening everywhere. Every galaxy Rubin studied had this same issue. There was not enough visible matter to explain how it was moving. That meant dark matter had to be real. It wasn't just an idea anymore. It was a necessary part of the universe. Now scientists had to accept a very strange truth. Most of the matter in the universe was invisible. Let's stop and think about that for a moment. Everything we've ever seen with our eyes, every star, every planet, every drop of water, every tree, every animal, every person, is made from what we call normal matter. But all of that normal matter adds up to just a small fraction of what's really out there. Most of the mass in the universe, more than 5 times as much as all the normal matter, is made of something we cannot see. Something that does not shine, does not glow, and does not interact with light at all. Imagine trying to solve a puzzle where most of the pieces are invisible. That is what astronomers and physicists are now facing. They know the pieces are there because they can see the effect, gravity pulling on galaxies, stars spinning at unexpected speeds, but they cannot see the pieces themselves. This is dark matter, and it's everywhere. It surrounds galaxies in giant halos. It weaves between clusters of galaxies like an invisible web. It is holding the universe together, even though we do not know what it is. Some people might ask, if we can't see it, how do we know it's real? The answer is simple: gravity. Dark matter has mass, and mass causes gravity. We don't see dark matter directly, but we see what it does. We see its influence. We see its footprints, even if we cannot see the feet. In this way, dark matter is like wind. We cannot see the wind itself, but we can see the trees moving, the leaves dancing, the clouds drifting. We know the wind is there, not because we see it, but because we see what it does. And so, our understanding of the universe began to change. We once believed we understood the cosmos because we could see the stars. But now we know. The stars are just a small part of the story. They are the glowing decorations on a much larger, much darker structure. What we see is not the whole picture. What we see is not even most of it. To truly understand the universe, we must look not just at what shines, but also at what hides. We must learn to see the shadows in the cosmos. Chapter 2. The Case of the Missing Mass. What happens when the math stops working? You go looking for what's missing. Now that astronomers had discovered something invisible was affecting how galaxies moved, the next step was to find out just how much of this unknown stuff was really out there. And the deeper they looked, the stranger the numbers became. You see, in science, we don't just look at objects, we measure them. We weigh them, count them, study their motion, and ask questions like, how much mass is needed to keep this galaxy together? Or what kind of matter could cause this much gravity? When scientists tried to answer these questions, the numbers were shocking. They discovered that most galaxies had far more gravity than their visible matter could explain. This meant that there had to be a huge amount of hidden mass spread throughout the universe. Not just a little extra here and there, but 5 times more than what we could see. It was as if someone had walked into a room filled with balloons floating in mid-air and said, something invisible must be holding these up. So, scientists began looking not just at individual galaxies, but at the universe as a whole. They studied galaxy clusters, enormous collections of hundreds or even thousands of galaxies, and noticed the same thing. These clusters were staying together when, by all rights, they should be flying apart. They studied the way light from distant galaxies bent as it passed near massive objects. This bending, called gravitational lensing, is a prediction of Einstein's theory of general relativity. According to this theory, any mass, even if it's invisible, can bend light. And when scientists saw this light bending happening around seemingly empty regions of space, they knew there was mass there. Lots of it. They just couldn't see it. It was like shining a flashlight into the forest and seeing the light curve around something you couldn't see. Something big. You'd know that something was out there, even if it was hidden. Now, scientists had multiple independent lines of evidence, all pointing to the same conclusion. Most of the universe's matter was invisible. So where was this missing mass hiding? Some scientists thought maybe it was made of ordinary matter, just hard to detect. Maybe it was in cold gas clouds, small stars that didn't shine brightly, or black holes. These are things we can't easily see with telescopes, so they seemed like good candidates. But that idea didn't last long, because when scientists looked at the early universe using microwave radiation left over from the Big Bang, they could actually estimate how much normal matter had existed back then, and the numbers didn't match. The total amount of ordinary matter, even with all the hidden gas and dim stars added in, was still too small. There was simply not enough of it to explain what was happening in the present-day universe. So the missing mass had to be something else, something completely different from the matter we know. That's when a new idea began to form. Maybe this invisible mass isn't made of atoms at all. Maybe it's something entirely new. Physicists began calling it non-baryonic matter, meaning it isn't made of protons and neutrons like everything else we're familiar with. This type of matter wouldn't shine, reflect, or block light. It would barely interact with the matter we're made of. In fact, the only reason we know it's there is because of gravity. Think of it like this. Imagine walking into a dark room where you can't see anything. But then you start to feel a strong pull on your body, a force dragging you in a direction you can't explain. You can't see what's causing it. You can't hear it, smell it, or touch it. But it's definitely there, and it's strong. That's what dark matter is like. It doesn't interact with light. It doesn't bump into things the way normal matter does. But its gravity shapes the entire structure of the universe. This was no longer just a theory, it was a fact supported by countless observations. But even though we knew it was real, we still didn't know what it was. So scientists gave it a name that was honest and simple: dark matter. Dark because we couldn't see it. Matter because it had mass and pulled things with gravity. But naming it didn't mean we understood it. That's the mystery at the heart of this story. We've measured its effects. We've mapped where it should be. We've even built computer models of how the universe behaves with it. But the most basic question remained: what is dark matter actually made of? And so the search began, not just to observe dark matter, but to identify it, to find the particle, the field, or the force behind the mystery. To discover what the universe is really made of. That search would lead to new theories, new experiments, and the birth of a new kind of science, a science that studies what cannot be seen. But before we explore what dark matter might be, we must understand the candidates. We must enter a world of invisible particles, hidden dimensions, and possibilities we've never imagined before. Chapter 3: Wimps, Axions, and the Ghosts We Chase. When something hides so well, you begin to wonder, is it even matter, or is it something else entirely? By now, scientists knew dark matter was real. They had seen its effects, they had measured its gravity, they had mapped its presence around galaxies and across the universe, but no one had ever seen it directly. That was the puzzle. So the big question became, what is dark matter actually made of? To solve this, scientists turned to something they knew well: particles. Everything in the universe is made of tiny building blocks called particles. Atoms are made of protons, neutrons, and electrons. Light is made of photons. And the world of physics had already discovered dozens of other particles, some stable, some that exist for just a tiny moment. Physicists wondered, maybe dark matter is just another kind of particle, one we haven't discovered yet. So they began to imagine what kind of particle it might be. It had to have certain qualities. First, it had to have mass. That's how it creates gravity. Second, it had to be invisible to light. If it absorbed or reflected light, we would have seen it by now. Third, it had to be stable. If it decayed or broke down, we wouldn't have so much of it around after billions of years. These rules narrowed down the list, but they also opened up a world of strange new ideas. One of the first big candidates was called a WIMP. That stands for Weakly Interacting Massive Particle. The name says a lot. These particles would be massive, meaning they have weight, but they would barely interact with regular matter. They wouldn't collide with atoms or bounce off electrons. They would just pass through everything, like a ghost walking through walls. WIMPs were a favorite idea for many years. They seemed to fit all the facts. And best of all, if they existed, we might be able to detect them. So scientists built underground labs to look for them. Yes, underground. Deep beneath the Earth, in old mines or tunnels where cosmic rays and background noise can't interfere. Inside these labs, scientists set up special detectors, hoping to catch a rare moment when a WIMP might bump into an atom. But year after year, the detectors found nothing. Some began to wonder, maybe WIMPs don't exist after all. So attention turned to another strange idea: axions. Axions are tiny, far, far smaller than anything we've ever detected. Unlike WIMPs, they wouldn't be heavy. In fact, they'd be extremely light. But if there were enough of them, their total mass could still make up dark matter. Axions came from a different part of physics, connected to how certain particles behave in magnetic fields. What made them exciting is that they didn't just come out of nowhere. They were predicted by some theories trying to solve problems in quantum physics. If axions existed, they would explain more than just dark matter. So scientists began building experiments to look for axions too, using strong magnetic fields and sensitive detectors that could spot the tiniest flicker of light. Still, the results were silent. This led to even wilder ideas. Some thought maybe dark matter isn't made of particles at all, at least not in the way we understand particles. Maybe it's made of something called a hidden field, something that stretches across the entire universe, affecting gravity but never clumping into visible objects. Others suggested that maybe our theory of gravity is wrong, that maybe we don't need dark matter, maybe we just don't fully understand how gravity works over large distances. These were bold ideas. They shook the foundation of physics. But the search didn't stop. New experiments were launched in space and underground. Particle accelerators, like the Large Hadron Collider, smashed atoms together at incredible speeds, hoping to create dark matter particles in the lab. Radio telescopes scanned the skies for signals. Satellites mapped dark matter by watching how galaxies formed in the early universe. And yet the ghost kept slipping away. To this day, we don't know if dark matter is made of WIMPs or axions or something else entirely. We don't even know if it's one thing or many. But the chase continues. Every year our tools get better, our detectors grow more sensitive, and our questions grow deeper. We are hunting something that hides better than anything we've ever looked for. We are chasing a shadow, a whisper, a shape we can't define. But we are also learning. In searching for dark matter, we are not just asking what is the universe made of. We are asking a much bigger question. What kind of universe do we live in? And the answer might be more strange, more beautiful, and more mysterious than we ever imagined. Chapter 4: A universe that shouldn't accelerate. Gravity pulls things together, but the universe is not slowing down, it's speeding up. Why? Let's take a moment to imagine the universe as it was just after the Big Bang. In that first flash of creation, everything we know, all matter, energy, space, and time, burst into existence. The universe began to expand like a balloon inflating. Galaxies started to form. Stars were born. Light began to travel freely. At first, it seemed logical to think that this expansion would eventually slow down. After all, gravity pulls things together. The more matter there is, the more gravity there is to slow the expansion. Scientists believed that, over time, the universe's expansion would get slower and slower. Maybe it would even stop and collapse one day. That's what most physicists expected in the 20th century. They even argued over how much the universe would slow down, not whether it would. But then something completely unexpected happened. In the 1990s, two teams of astronomers were studying very distant supernovae. These are powerful explosions that happen when giant stars reach the end of their lives. They are so bright that we can see them from billions of light years away, even across time. Because they all explode in a very similar way, supernovae can be used like cosmic yardsticks. By measuring how bright they appear to us, astronomers can figure out how far away they are and how fast the universe was expanding when their light began its journey toward us. The teams expected to find that the expansion of the universe had slowed down over time. But that's not what they found. Instead, they saw that the universe's expansion was speeding up. Let that sink in. The universe wasn't just growing, it was growing faster and faster, like a car that keeps accelerating even though no one's pressing the gas pedal. This was completely opposite to what gravity should be doing. It was as if something was pushing space apart, stretching it faster and faster over time. But what could that something be? There was no obvious answer. To explain it, scientists had to introduce a new idea, something they called dark energy. Just like dark matter, dark energy doesn't shine or reflect light. It's invisible. But unlike dark matter, which pulls things together with gravity, dark energy seems to do the opposite. It pushes space apart. Imagine placing an apple on a table. If gravity alone was acting, the apple would stay put. But with dark energy in the mix, it's as if something invisible is slowly nudging the apple farther and farther away, even though nothing is touching it. So what is this dark energy? No one knows for sure. That's the honest truth. But here's what we do know. Whatever it is, it makes up most of the universe. Let's look at the numbers. The stars, planets, gas, and everything we can see, that's only about 5% of the universe. Dark matter, the invisible substance that pulls galaxies together, makes up about 27%. And dark energy? It makes up the remaining 68%. That means nearly 3/4 of the universe is made of something we can't see, can't touch, and don't understand. And yet, it's this something, this dark energy that controls the universe's fate. Some scientists think dark energy might be something called the cosmological constant, a term Albert Einstein once added to his equations, then later removed. He introduced it because he believed the universe was static, not expanding or contracting. When Hubble discovered the universe was expanding, Einstein called the constant his biggest blunder. But now, the idea is back. Maybe Einstein was right after all, just for the wrong reason. Others believe dark energy might be a new kind of field, something that fills all of space like an invisible fluid. Or maybe it's a property of space itself, something that appears naturally as the universe grows. Still others think our understanding of gravity might need to change. Maybe gravity behaves differently over very large distances. Maybe our equations work well in our solar system and nearby galaxies, but not across billions of light years. Whatever the answer is, one thing is clear. The discovery of dark energy changed everything. It told us that the universe is not slowing down. It's rushing forward into the future, faster and faster. It told us that the cosmos is more mysterious than we ever imagined. And it told us that our story, the story of the stars, of galaxies, of life itself, is being written in the middle of something we don't yet understand. So now, we face a new mystery. Dark energy is not just a part of the universe, it is the universe. And until we understand what it is, we cannot truly know where we came from or where we are going. Chapter 5: The Silent Architects of Structure. If the universe were a city, dark matter would be the skeleton of its skyline. In the vastness of space, stars and galaxies are not scattered randomly. They are organized, arranged in patterns, threads, and clusters that stretch across billions of light years. From afar, the cosmos looks like a vast web, galaxies forming along thin filaments, great voids lying in between, and massive clusters sitting at the intersections like cosmic cities. This structure is not a coincidence. It's the result of deep, invisible forces at work over billions of years. But here's the mystery. If we only had the matter we can see, stars, planets, the universe wouldn't look this way. The structures we see today, the enormous galaxy clusters and the complex web of cosmic filaments, could never have formed if ordinary matter were the only ingredient. There simply wouldn't have been enough time or enough gravity to pull everything together. So, how did the universe become so structured? The answer lies with something we cannot see: dark matter. Long before stars formed, long before the first galaxies lit up the universe, dark matter was already shaping the landscape. It was quiet, invisible and cold, but its gravity was strong. And in that early silence, it began to pull. Tiny ripples of dark matter formed shortly after the Big Bang. These weren't galaxies yet, just small clumps of invisible mass. But over time, these clumps grew. They pulled in more dark matter, and soon they began to attract ordinary matter too. Like scaffolding on a building, dark matter created a frame, a structure, onto which visible matter could attach. Gas fell into the gravitational wells made by dark matter. Stars were born in those wells. Galaxies began to spin inside them. Dark matter never lit up the sky, but it shaped the stage where everything else could shine. Today, astronomers use powerful computers to simulate how the universe evolved. When they include dark matter in their models, something amazing happens. The simulations begin to look like the real universe. Galaxies form in the right places. Clusters grow. Filaments stretch across space. Voids appear where they should. But when dark matter is removed from the model, the universe looks wrong. Too smooth, too simple. The structures never form. The stars never gather into clusters. The web never weaves. That's how scientists know. Dark matter is the silent architect behind the universe's large-scale design. Its gravity is the blueprint that shaped the cosmos from the very beginning. And even now, that invisible framework is still holding everything together. Every galaxy we see, including our own Milky Way, is sitting inside a vast halo of dark matter. These halos are far larger than the galaxies themselves. The stars are just a tiny core at the center. The real mass lies in the shadow. You can think of a galaxy like a pearl inside an oyster. The shining part, the stars, is beautiful and visible. But the dark shell around it is what protects it, shapes it, and holds it in place. And it's not just individual galaxies. Even giant galaxy clusters containing thousands of galaxies are wrapped in dark matter halos. Without these halos, the clusters would fly apart. Gravity alone from ordinary matter couldn't hold them together. But dark matter doesn't just explain what we see, it also explains what we don't see. Between galaxies lie huge voids, enormous regions of nearly empty space. These voids exist because matter has been pulled into the filaments and clusters shaped by dark matter. The voids are the result of what dark matter did not claim. In a strange way, dark matter defines the universe not only by its presence, but by its absence. It creates the form, the contrast, the map. And yet, despite all this influence, dark matter remains completely silent. It doesn't glow, it doesn't interact with light, it has no color, no temperature, no texture, but its gravity speaks volumes. Without it, there would be no galaxies, no stars, no planets, and no people to wonder about it. It has shaped the universe quietly, patiently, invisibly, and even now, it surrounds us. The Earth moves through a dark matter halo every second of every day. Our solar system floats in it like a speck in a vast, invisible ocean. We can't see it, we can't touch it, but we are part of it. In this grand cosmic structure, built by forces we cannot detect directly, we find ourselves asking not just what the universe is, but what made it possible. And the answer, more often than not, points back to the dark. Chapter 6. The Cosmological Balancing Act. The universe is expanding, but not wildly. Structures are stable, but not frozen. Somewhere in between chaos and stillness lies a delicate balance. From the earliest moments after the Big Bang, the universe has been expanding. That much is clear. But what's far more fascinating is that the expansion didn't happen in a messy, uncontrollable way. Galaxies formed, stars gathered into orderly spirals, clusters of matter came together. And yet, all of this happened while space itself was stretching and growing. So here's the question. How did it all hold together? This is where the idea of cosmic balance comes in, a balance between opposing forces that, for billions of years, have shaped the universe into what we see today. On one side of this scale, there is gravity, the great gatherer. Gravity pulls matter inward. It wants to collapse gas into stars, gather stars into galaxies, and gather galaxies into even larger structures. It is the force that creates clumps, forms, and shapes. On the other side, there is expansion, driven by something deeper, something that causes space itself to stretch. Left unchecked, this stretching would tear galaxies apart, scatter stars, and leave the universe cold and structureless. But somehow these two cosmic forces have been kept in check. Not perfectly, but in a kind of dynamic dance. It's a bit like heating a pot of water. If the heat is too strong, the water boils violently. If it's too weak, nothing stirs. But in just the right conditions, patterns form. Swirls rise and fall. A complex but stable motion appears. The early universe was like that, a fragile blend of conditions, where expansion didn't completely erase structure and gravity didn't fully pull it all inward. And here's where it becomes even more curious. This balance isn't just a lucky accident. It seems to be precisely tuned. If the amount of dark matter had been even a little bit less, galaxies wouldn't have had enough gravity to form. Matter would have stayed spread out and thin. If dark energy had been just slightly stronger, the universe would have expanded so fast that stars would never have come together. If ordinary matter had been slightly more abundant, the universe might have collapsed under its own weight before anything had a chance to evolve. Everything, the density of matter, the strength of dark energy, the rate of expansion, seems to exist on a razor's edge. Cosmologists call this phenomenon the fine-tuning problem. It refers to the idea that the values of key cosmic ingredients had to be almost exactly what they are, not just similar, but precisely balanced, in order for complex structures and life itself to exist. It's a bit like walking a tightrope across a canyon. Step even slightly to one side or the other, and everything falls apart. Now, there are many ways to interpret this strange precision. Some scientists believe that this balance is simply built into the laws of physics. that our universe just happens to be the kind where the numbers worked out this way. Others suggest something more mind-bending, that there may be other universes, a vast multiverse where each one has different values for dark energy, gravity, and matter. In this idea, most universes are sterile and lifeless, but we live in the one where conditions allow galaxies, stars, and conscious observers to exist, because we had to live in that kind. Still, these are ideas, not proven facts. What is certain is this: our universe behaves as though it has been balanced, held in tension between collapse and runaway expansion, just enough for structure to emerge, but not so much that it tears itself apart. And that balance didn't stay still. Over billions of years, the scales have shifted. In the early universe, matter, both ordinary and dark, played the dominant role. Its gravity slowed expansion, helped form galaxies, and gave rise to cosmic structure. But as the universe expanded, matter grew thinner, more spread out. Meanwhile, dark energy, which does not thin out, remained steady. Slowly, it began to take over. At some point, around 5 billion years ago, dark energy surpassed matter. Since then, it has been driving the expansion faster and faster, pulling space apart more forcefully with every passing moment. It's a changing balance, a cosmic tug-of-war where one side is gradually gaining strength. We live right in the middle of this change, at a time when galaxies still form, but the universe is beginning to race ahead. A time when matter still clumps together, but the fabric of space is starting to pull it apart. This is the cosmological balancing act, a delicate arrangement of forces, energies, and conditions that allowed complexity to emerge and continues to shape what the universe will become. And as we look deeper into space and farther back in time, we see the echoes of this balance written across the stars, in the motion of galaxies, in the shape of cosmic filaments, in the cold glow of the early universe. We are not just witnessing the universe. We are living inside a puzzle where every piece fits, not perfectly, but precisely enough to give rise to something extraordinary. And that brings us to a deeper question. If the universe is so finely balanced, was it always meant to hold together? Or is it just passing through a moment of harmony before the scales shift forever? Chapter 7, The Fate of Everything. If the stars are still burning and galaxies are still forming, does that mean the universe will go on forever? Or is everything moving toward an end we cannot yet see? The universe is not still. That much is certain. Galaxies are drifting apart. Space is stretching, and behind it all, something is quietly pushing. Unseen, unstoppable, steady. We call it dark energy. It's not just a mystery, it's a force that is reshaping the future, and that future might look anything like the world we know now. For a long time, scientists thought the cosmos might collapse. That gravity, pulling on every galaxy and every atom, would one day slow the expansion, maybe even reverse it. The idea was called the Big Crunch, a time when all matter would fall back inward, heating up, compressing, and possibly leading to another explosion, a new beginning. But the discovery of accelerated expansion changed everything. If the expansion of the universe is getting faster, not slower, then a collapse becomes less likely. Gravity is no longer in control. The universe is not pulling itself together. It's rushing outward, as though being driven by something far stronger than we expected. This raises a haunting question. What happens if the universe keeps accelerating forever? One possible outcome is what cosmologists call the heat death, also known as the Big Freeze. In this scenario, the universe keeps expanding endlessly. Galaxies move farther and farther apart. Stars run out of fuel and die. New stars stop forming. The night sky, once filled with light, grows dimmer. Trillions of years from now, only black holes and cold remnants will remain. Even black holes eventually may vanish, slowly evaporating through a strange process called Hawking radiation. What's left is silence, a vast, empty, dark universe. Not destroyed, but exhausted, stretched so thin that nothing more can happen. No new stars, no new warmth, just particles drifting in endless night. And the strangest part? This future is not dramatic, it unfolds slowly, quietly. It is the final breath of a universe running out of energy. But there are other possibilities too. Some scientists wonder whether dark energy might grow stronger over time. If it does, the expansion won't just continue, it will accelerate so much that it begins to tear things apart. This scenario is known as the Big Rip. In a Big Rip universe, everything is pulled apart, not just galaxies, but stars, planets, atoms, and even the fabric of space itself. First, the galaxies drift away from each other. Then, stars inside galaxies are torn from their orbits. Then planets are ripped from stars. Moons are lost, worlds are unmade. Eventually, even atoms are pulled apart. The bonds that hold matter together are stretched until they break. And then, the universe itself unravels. This would be the most violent end. Not a freeze, not a collapse, but a shredding of reality. There's also the possibility of a cosmic phase transition, something sudden and unexpected. Just as water can suddenly freeze or boil, some physicists think the universe's fabric could undergo a transformation. In this version, a different kind of energy, buried deep in the vacuum of space, could trigger a new state of physics. In an instant, the universe as we know it would be rewritten. The laws of nature might change, matter might dissolve, light might behave differently. This idea is called a vacuum decay, and while it sounds like science fiction, it's a serious possibility based on some interpretations of quantum field theory. And yet, for all these bold and chilling theories, one thing remains humbling. We simply don't know. We live in a universe that is 13.8 billion years old. We've only been watching it closely for a few decades. Our perspective is brief, our understanding is still growing. But what we do see, clearly, unmistakably, is that the universe is evolving. It is not static. It is not eternal in its current form. And whatever fate awaits, it will not come quickly. There is still time. Stars still shine. Galaxies still dance. Life still wonders. We are living in what cosmologists call the stelliferous era, the age of stars. It's a golden chapter in cosmic history, where the lights are still on and the sky is still alive. But this chapter, like all others, will end. It may take billions, trillions, or even longer. But the future is already being shaped by the forces we see today. Forces like dark energy, whose full nature we still cannot name. In the end, the fate of the universe depends on the very thing we understand the least. And so we look forward, not in fear, but in awe, knowing that we are witnessing a small slice of a much greater story. A story that will stretch far beyond the stars we see, into silence, into the dark, into whatever comes next. Chapter 8. The Edge of Knowledge. Somewhere out there, beyond what we can measure, beyond what we can test, lies the unknown. We stand on the shoreline of truth, looking out at a sea we cannot yet cross. Science is a journey, a path that moves forward with each new observation, each bold theory, each quiet discovery made under dim lights and long nights. But every journey eventually reaches a horizon, a place where the ground beneath your feet ends and the rest remains out of reach. That is where we now stand. When it comes to dark matter and dark energy, we've come far. We've traced their effects through galaxies and light. We've mapped the motion of stars and the shape of space. We've designed machines to wait for a whisper from the dark. But still, we do not fully understand what these things are. We only know what they do. And so we arrive at the edge of knowledge. Here, science meets its limits. Not because we've failed, but because the questions have become deeper than the tools we've built to answer them. For example, what if dark energy isn't just an extra ingredient in the universe? What if it points to something broken in our understanding of gravity? Einstein's theory of general relativity has passed every test we've thrown at it. It describes how matter bends space. It explains the orbit of planets, the bending of light, and the expansion of the universe itself. But it's also a theory built on observations from a time before dark energy was discovered. So some physicists ask, what if we need a new theory of gravity? One that changes on large scales. One that explains cosmic acceleration without needing dark energy at all. These ideas fall under the banner of modified gravity, alternative models that adjust the rules of space-time to explain what we see. So far, none of these alternatives has matched the data better than Einstein's equations. But the very fact that we're asking the question shows just how far the mystery reaches. We are also reaching the limits of the standard model of particle physics, the theory that describes all known particles and their interactions. The Standard Model is one of science's greatest achievements. It predicted the Higgs boson, explained the behavior of quarks, and united electromagnetism with the weak nuclear force. But it has a hole in it. It does not contain dark matter, it does not explain dark energy, and it has no place for gravity. So at the edge of knowledge, another dream rises, the dream of a theory of everything. A framework that would unify gravity with quantum mechanics, that would tie together the strong, weak, electromagnetic and gravitational forces into a single elegant equation. Physicists have tried. Ideas like string theory and loop quantum gravity have offered possible paths forward. They propose hidden dimensions, vibrating strings, or a foamy, flickering structure to space itself. But these theories are difficult to test. They require energies far beyond what our particle colliders can reach. They predict phenomena we cannot yet observe, and so they remain just out of reach, shimmering at the horizon like islands seen through mist. There is also the edge of technology. Our instruments are powerful, but they have limits. Our telescopes can't see past the cosmic microwave background, the fog of light from when the universe was only 380,000 years old. Beyond that, the universe is opaque to photons. If there are clues hidden in those first moments, in the birth of matter, the inflation of space, the creation of dark energy, they may lie forever outside our view. New ideas are emerging, using gravitational waves instead of light to see deeper, or detecting the faint pattern of neutrinos left over from the Big Bang. But these approaches are in their infancy. The edge is near. There is also the edge of language, the human challenge. As we reach into these vast abstract ideas, particles that don't exist in our everyday world, energies that stretch across cosmic distances, we find that even words begin to fail. How do you describe something that has never been seen, never been touched, never been confirmed? We use metaphors. We call them shadows, winds, fields, or oceans. But we know that these are only approximations, tools to guide understanding. Behind them lies something stranger, quieter, harder to hold. And yet the edge is not the end. It is the invitation. It tells us that there is still more to learn, more experiments to build, more theories to test, more ways to ask the universe what it is made of. A century ago, we didn't know about galaxies outside our own. A few decades ago, we didn't know the universe was accelerating. Every generation finds its edge and then pushes against it, with questions, with curiosity, with courage. So while we may not yet know what dark matter is, while dark energy remains unexplained, while gravity and quantum mechanics still resist unification, we continue to move forward. We peer through telescopes not just to see stars, but to see beyond them. We build detectors not just to find particles, but to find meaning. We write equations not just to calculate, but to understand. This is the edge of knowledge, and beyond it lies the future. Here is the final chapter, the cosmic perspective. We are small, but in our questions, in our wonder, in our willingness to reach for the unknown, we are vast. Look up at the night sky. The stars may seem still. The galaxies may seem frozen in their silent glow. But behind them, beyond the shimmering points of light, there is motion. There is tension. There is something immense and invisible that holds the structure of the universe together, and something else entirely that is pulling it apart. We have spoken of dark matter. We have spoken of dark energy. We have followed the evidence. We have built the tools. We have traced the patterns of gravity and the slow stretching of space. And now, standing at the far edge of what we know, we are left with something that goes beyond science. A new kind of perspective, the cosmic perspective. It is not just about facts or equations. It's not about telescopes or particle detectors. It is about us, about the human desire to understand where we are and what we are part of. We live on a tiny planet, orbiting an average star, in one corner of a galaxy among billions. And yet, from this small place, we have uncovered truths that stretch across the universe. We have revealed that the stars are not just lights in the sky. they are the past. That space is not empty, it is full of hidden matter and restless energy. That the universe is not a fixed stage, it is a dynamic, unfolding story. This perspective changes how we see ourselves. It humbles us because we are not the center of the universe. It empowers us because we can still comprehend the forces that shape it. Imagine that. A creature made of atoms, existing for a flicker of time, asking questions about things as vast as galaxies and as subtle as quantum fields. That is the miracle of human consciousness, the miracle of curiosity. The mystery of dark matter and dark energy reminds us that our knowledge is incomplete. It tells us that the universe is deeper and more complex than any one theory or model can explain. And that is not a failure, it is a gift, because it means there is still more to discover. It means that wonder is not just for children. Wonder is for anyone who looks up and feels that quiet pull, the one that says, there's more out there. There are deeper truths waiting to be found. There are new laws of physics hiding in the silence between galaxies. There are answers written in the structure of space and time, waiting for minds bold enough to ask the right questions. And maybe, most beautifully of all, there are mysteries that will never be fully solved. Not because we are too small, but because the universe is endlessly rich. A cosmos that reveals itself slowly is a cosmos worth exploring forever. Dark matter and dark energy are not just puzzles for physicists. They are reminders that the universe does not owe us understanding, and yet somehow it gives us clues. It whispers, it leaves trails, it invites us to listen. In that sense, the search itself becomes something sacred. Not in a religious way, but in a deeply human way, a quiet recognition that to wonder is to be alive. So as we close this journey, we are not closing a mystery. We are stepping into a deeper one. The stars still shine, the galaxies still drift, space continues to expand. And somewhere in all of it, we remain, watching, questioning, reaching, with eyes that seek the invisible, and minds that dare to dream of everything we cannot yet explain. This is the cosmic perspective, and it is ours.